In this video I will show you how to turn the rangefinder data into world coordinates that you can later map and visualize. Now we are using the line following controller that we developed in previous labs, and what you should have is a robot going around the circular environment. You should have set up the rangefinder and place some objects in the environment that help you to make sense of the data that you collect. What I've also done already is I imported NumPy as NP, and I imported pyplot from the matplotlib library as PLT. If you don't have that yet, please install it using pip or Google how to do that. It is important to be able to visualize data, and it will make your life a lot easier. What we have also done is we have introduced code that is able to retrieve a range image using lidar.getRangeImage. The lidar has been enabled here, and very important, I had to enable the point cloud functionality so that the lidar actually works. Alright, so what we have is we have all the ranges in the ranges list. I've also created a list of angles which go from pi to minus pi. So let's look at this real quick. In the robot coordinate system, we established that the first ray in the array is pointing backwards. This is angle 0, so this is either plus 180 degrees or minus 180 degrees. Now, we also established that the 90th entry is actually pointing to the left. That means the lidar rays are stored in a clockwise fashion. They start here with the 0th element. This is the 90th element. This is the 180th element. Now the rotation convention is counterclockwise, which you can see when looking at the z-axis. And we therefore want to have the first entry to be at 180 degrees, the 90th entry at 90 degrees, the 180th entry at 0 degrees, and then the last entry at minus 180 degrees. So this is why we created this array here, and I can now write a for loop to go through these two arrays and collect the data. So I use something like this, an index and an angle. So now I get an angle from angles, and I get the index in I, and I can do something like this and write down xi and yi to compute the coordinates in the robot coordinate system. And if you followed along, you will already know how to do that. I use the ranges at the eth entry, and I multiply this with npi and numpy cosine of the angle, and I do the same for yi, but multiply it with sine of angle. And this can be easily seen when you look at the robot coordinate system. I have this ray looking forward at 0 degrees. Now all of it contributes to the x-axis. Cosine of 0 is 1. Sine of 0 is 0, so that means the whole ray will be projected onto the x-axis, and this looks about right. Now what I can also do is I can store those in a list like this, and let's call this Rx of R, so we know that these things are in the robot coordinate system, and we create two empty lists, and I can now append them to this list yr. Now I should have two lists with all of the values of xi and yi in here, and I can plot them. And the way to do this is I say plot of x and y, and I want to plot these as points, otherwise there will be connected lines which will be difficult to visualize, and I can say plot show. Of course I need XR. And so here it goes. I see an image of all of the sensor rays that I've been plotting. I have the robot looking this way along the positive x-axis, and around 70 centimeters along the x-axis I see the final wall. I see the biscuit box to the right, I see the honey jar, I see another biscuit box, and I see the outside of the arena in the back. Now that we have successfully visualized how to plot the points that the laser rangefinder records in the robot coordinate system, we can turn them into world coordinates, and for that we introduce a new data structure, something like XW, YW, where the W stands for world, and we can now append all of our readings to this new array, like so, and YW append. And now what we need to append is not just the XI and YIs, but we have to turn them into world coordinates. The way we do this is using a rotation matrix, and the rotation matrix has the following form. We have the first entry and multiply with XI, then the second entry and we multiply with YI, and now we add the position of the robot in the world, which we computed earlier using odometry, to be XW. And just to make sure we have these equations there down here, we took the forward motions in the X coordinate frame of the robot and transformed them into world coordinates. And this was easy because we didn't have any motion along the y-axis. Now we need a full transformation matrix, and doing this is a great exercise to actually fully understand this, and that's why we are doing it together here. So we do it for the y coordinate as well. We have the second row of the matrix and we multiply with xi, and the last entry, which is multiplied with yi, and we add YW. Now have a close look at this. If you stare at this long enough and you think about XI and YI to be a vector to the right of this matrix, you have a matrix A, B, C, D in the center, and then we are adding the world coordinates later on. Now what are these entries A, B, and C and D? At the time we talked about looking at the projection of the coordinate system of the robot to the coordinate system of the world, and we have that down here in the bottom right. If you don't see this, you can make this appear in optional rendering, show coordinate system. This will get you this tiny thing down here. And now we can think about how the coordinates of the robot project onto the coordinates of the world. So the first entry of this matrix was the dot product between the x-axis of the robot coordinate system and the x-axis of the world coordinate system. The dot product is the length of these vectors, which was 1, times the cosine of the angle between them. Now the angle between them is actually theta, because the robot has been rotating by theta degrees to the left. We have initialized this here, which is 90 degrees. So we can actually just write np.cosine of theta down here. This is our first entry. Now the second entry is the dot product between the x-axis of the robot and the y-axis of the world coordinate system. And this is a little harder to see, and maybe it helps to turn the robot by a little bit to the right. Now we have around 80 degrees for theta. Now what is the angle between the x-axis and the y-axis? It's around minus 10 degrees. So what we need to do is we have to subtract from 90 degrees, or actually we use theta, which is around 80 degrees, and we subtract 1.57, which is 90 degrees. And what we should get is minus 10 degrees, and that is exactly what the angle between the x-axis and the y-axis is. Now we can move over to the next entry, which is the dot product of the y-axis with the x-axis of the world coordinate system, and this is theta plus 90 degrees. So you see here I have 90 degrees, and then I go a little more, which is our theta, which is around 80 degrees. So now this makes sense. Now the last entry, we look at the y-axis projected onto the y-axis, and here the angle is just theta. Now I filled up all the entries of the matrix, and maybe we do it like this to make it look a little nicer so you can see really what's going on. So we have the matrix rotations, and now we can plot these by simply replacing the R with a W, and we should be able to see our result. Let's run this. And here you go. You see the robot is at 0, 0, and it sees the arena wall to its back along the negative y-axis. In front, around 75 centimeters, is the arena wall. We see the cookie biscuit box, and we see the biscuit box to the right. Now we can also run this while the robot moves. For that we need to make the plot interactive, and you probably wondered already how I was able to plot the plot above the Webots window. I wasn't. I actually faked this and recorded it and then overlaid it in the video editing software. What you need to do is you have to make the window, restore the window to a normal size, and then you can actually see Webots and the PyPlot window at the same time. So to make the plot interactive, you need to do two things. First, you have to enable interactive mode. Then you have to add a little pause after every time you plot something, and now you should be able to see the robot moving on the map. Now the robot starts moving, and you see it goes slower and slower as the plot is filling up with data. This is obviously not a good way to create a map. We will talk about this in the next part of this course, however.